Okay, in this video we're going to differentiate x squared plus y cubed equals 1. And right now this is an implicit function because y hasn't been isolated by itself. So the point of this video is that we don't want to always have to isolate y by itself, because sometimes it's a lot of work and sometimes it's even impossible to isolate y by itself. But in our first intro here, of course, it's pretty easy to isolate y by itself, so we're going to do that before we go ahead and differentiate this relation or this function implicitly. We're going to use our traditional techniques and get y by itself and differentiate this function. And then hopefully we can develop another option that will serve us better in other situations as well. So get y cubed by itself, which is, like I say, not much work because we just need to subtract x squared from both sides. And then we need a cube root of both sides of that equation. That'll give us the cube root of 1 minus x squared. So of course that is the same as 1 minus x squared raised to the power of a third. And now we're ready to differentiate this function, because y prime is going to be the chain rule, an application of the chain rule here. The power function, 1/3, needs to be differentiated first, with the 1 minus x squared trapped inside. So a third comes down, subtract 1 from a third to get negative 2/3. And don't forget to multiply by the derivative of the inside function, which is negative 2x. So let's clean up our derivative a little bit and get rid of, and I guess try to get back to roots, because that's where we started. Once I have our function written explicitly, and that's of course the term we use if we do get y by itself. So our derivative, what can we do? We can write the prime, I guess is a good idea. Let's leave the minus 2x up top. And then on the bottom, of course, we have that 3 from the fraction of a third. And we'll write our negative exponent down below. So that's 1 minus x squared to the power of 2/3. Let's switch this back to a root. So minus 2x on the top, 3 on the bottom. And we have a cube root, of course, with that bottom denominator of a 3 of 1 minus x squared. And I can square the radicand there. I can square that 1 minus x squared, but I'm actually going to opt to square the whole cube root. Of course, there's two ways you can deal with that square in the numerator of our function. And the reason I chose to write it that way is because if we see our explicit equation above, y is the cube root of 1 minus x squared, I think it should be fairly obvious in my derivative that we could actually, if we wanted to, rewrite it another way. Now, up until this point, you would never entertain rewriting your derivative once you have it, and it's a function of x. You can input x values, and you can get tangent slopes, of course. But remember, we're trying to set up implicit differentiation here. So if we realize that cube root of 1 minus x squared is just y, I guess I better write the rest of this first, that we really just have y squared on the bottom. 3 times y squared on the bottom. I guess I can use the white here, because of course y was equal to the cube root of 1 minus x squared. So when we perform implicit differentiation, we are going to get our derivative. It's going to look exactly like this thing. Okay, so there it is. We rewrote our implicit function as an explicit function. We just relied on our chain rule, and we got our derivative. And I went one step further as a setup for the rest of this video, and we're going to look at how we can differentiate this this function without getting y by itself. And of course, our derivative will end up precisely as it shows here, as minus 2x over 3y squared. Okay, so now let's look at implicit differentiation. We're going to differentiate this implicit function without getting y by itself. So we can apply the differential operator, d over dx, to both sides of an equation. That's the first step. And put some brackets there on that one. So what do I have inside those brackets? Well, of course, I have x squared plus y cubed on the left-hand side, and I just have the number 1 on the right-hand side. So if I have the derivative on the left-hand side of a sum, of course, that is the sum of the two derivatives. differential operators set up here first. So the derivative of a sum is the sum of the derivatives. Derivative of x squared, derivative of y cubed, and the derivative of 1. Well, two of those are pretty straightforward, so maybe we'll do those first. The derivative of x squared, of course, is 2x. We're going to leave this for the time being. And the other super easy derivative is the derivative of 1, since 1 is a constant, is 0. So the crux of the situation here is dealing with what the derivative with respect to x is of y cubed. Well, remember, previously we took the time to get y by itself. And we ended up with y written as a function of x, which was the cube root of 1 minus x squared. Well, hopefully you can start to recognize something with the derivative of y cubed. If I go one more step here, and rewrite the rest of our equation, is that I'm taking the derivative of y of x cubed. Now, just to remind yourself, even though we didn't solve for y and isolate y by itself, we do know y is a function of x. So when we're differentiating a function of x trapped inside this cube, you can probably guess what's going to happen. Yes, we're going to have to use the chain rule. So we'll copy that. And then when we're differentiating y of x all cubed, we first have to do the power function. So the 3 comes down, and then we subtract 1 from 3. Our y, which remember is a function of x, is trapped. So we have to finish this off. The chain rule by multiplying by the derivative of the inside function, which was y of x, which we'll write as y prime of x. You can use Leibniz notation if you wish, but I think y prime of x would be a little more straightforward. And there it is. There's our derivative found using implicit differentiation. So of course what we're interested in is y prime of x. So now we just get y prime of x by itself. And this will be our derivative that we and hopefully it matches what we had previously. So how do we get y prime of x by itself? Well, we're going to subtract. Maybe I better do this in 2 steps. I'll write this first. That was 3 times y of x squared. So first step, we'll subtract 2x from both sides on this equation, and then it's probably pretty obvious what we need to do. We need to divide both sides of this equation by 3 times y of x squared. And that will leave us with y prime of x equal to minus 2 of x all over 3 times y of x squared. And there's our derivative, and of course that matches pretty much exactly what we had before. The only difference is we have a y of x here, and remember why I wrote it as y of x was to remind us that we needed to use the chain rule when we're differentiating y cubed with respect to x, because we really have a function of x trapped inside of a cube. So let's drop our y of x at this point and clean up our derivative. It'll match exactly what we found previously. This will be y prime. We know it's a function of x, at least if we write it explicitly. And then it's going to be minus 2x all over 3 times, get rid of the of x, y squared. And I guess I can put brackets around that if that helps you see. What I did, I just dropped the of x, and of course that matches our derivative. And that's not a huge time saver in this situation, remember, but of course we need to get used to differentiating an implicit relation, because sometimes it's a lot of work to get y by itself. So at least this justifies that it does work. It gives us the same derivative that we found, I guess, through our more familiar means. So there's our introduction to implicit differentiation. We'll move on the next few videos looking at some more examples.